Hi everyone, so we're back again and today we are looking at the natural numbers. So you might recall that our natural numbers are our counting numbers. They are from 1, 2, 3, so on. So whole positive numbers, our whole numbers that are positive are our natural numbers. So a few definitions, and these are things that you would have already known for a number of years. So first one, a natural number A is a factor of a natural number B if there exists a number K such that B equals AK. So what we're saying is that our value here A is a factor if I can multiply it by something to get the other number. Now, we would have done this, you would have an idea of this easily. So if we're wanting to, for the number 12, a factor of 12 is 3. And how do we know that 3 is a factor of 12? It's because there exists another number K that I can multiply by something, in this case 4, to give me 12. So that's what this definition is saying, that for something to be a factor, I need to be able to multiply it by another natural number. And I'm sure you already had a knowledge of what factors were. Our prime numbers are a natural number greater than 1, So 1 is not a prime number. So prime numbers, if its only factors are 1 and itself. So 13 is a prime number because the only things I can multiply to get 13 are 13 times 1. The only factors are 1 and itself. A composite number, if it can be written as a product of two natural numbers that are greater than m and less than 1. So m is a composite number if we can write it as something like, so number 12 is a composite number because it can be written as a product of 3 times 4. A highest common factor of two natural numbers is the largest number that is a factor of both A and B. So if I had the number 12, the factors there, the numbers I can multiply to get 12, 1, 2, 3, 4, 6, and 12. For the number 16, the factors are 1, 2, 4, 8, and 16. The biggest number common to both of them there is the number 4. So that means that our highest common factor would be 4. And I know these are all terms that are familiar to you. A natural number is a multiple if there exists a number that I can multiply something to get there. So a multiple of 4 is the number 16. 16 is a multiple of 4 because, that's not a good choice. Let me go instead. 20 is a multiple of 4 because it is possible to multiply 4 by something else, another natural number, to get 20. So looking at this, we can say 20 is a composite number. 20 is a multiple of 4. We could say 4 and 5 are the factors of 20. So these things do go backwards and forwards. The lowest common multiple of two numbers is the smallest natural number that's a multiple of both of them. So for the numbers 4 and 6, the multiples of 4 are 4, 8, 12, 16, so on. Multiples of 6, 6, 12, 18, and so on. 12 is the smallest number that is in both lists. So 12 is our lowest common multiple. Now, I don't think that any of that is new. It's just written in a much more formalized manner than the types of definitions you usually read. So let's keep going and see some more about our natural numbers. The fundamental theorem of arithmetic says that every positive integer, so that's the same, every positive integer, that's the same as saying every natural number, except one, can be represented in exactly one way, apart from rearrangement, as the product of one or more primes. So again, let's look at our number 12. 12 could be written as 2 times 2 is 4 times 3. It's written as a product of primes. If I'm wanting to write this as prime numbers, there is no other way to write that. 12 equals 6 times 2. That is not a product of primes, so that doesn't work. Except for rearrangement, because this could be written in other ways, but because multiplication is commutative, it can be written in any order. All of those are equivalent expressions. So that's what this fundamental theorem of arithmetic says. Every number can be written in exactly one way as a product of one or more primes. That even holds true for prime numbers. The prime number 13, a product of primes, is just going to be 13, or 13 times 1, I suppose, although technically that's not a prime number. It already is made up of just primes. So, when we need to give the prime decomposition of a number, that means that we're wanting to break it down into those prime factors. Some of you might remember doing factor trees when you were in year 7 or in primary school. And factor trees would work for this, but they're quite messy to write out for numbers that can be large. So before we get on to this one, let me just show you a smaller example. Say we had the number 24. If I was doing a factor tree for this, you might remember saying, what two numbers can I multiply to give 24? Let's say I'm doing 6 times 4. We look at these, and you can start with anything. 2 times 12 would have been fine to start as well. 6 and 4, neither of those are prime numbers, so I split it up again. 6 is the same as 3 times 2. 4 is the same as 2 times 2. These are now all prime numbers, so I have 2 times 2 times 2, 2 cubed times 3. So this is our factor tree way of doing these questions. The other way we can do it is using repeated division. And this is sometimes a better method when we're doing here. Repeated division, I've got my number 24. What can I divide 24 by? And I want to always divide it by prime numbers. So I'm always looking for primes this time. A prime number I can divide 24 by, I know, is 2. 2 goes into 24 12 times. What's a prime number I can divide 12 by? 2 goes into 12 6 times. Again, a prime number is 2. 2 goes in 3 times. What's a prime number that goes into 3? Just 3. So this here on the left side, these are my prime factors. So again, I have 2 cubed times 3. And we can apply this same strategy to larger numbers. So I think that this strategy of repeated division is probably the way to go when we have large numbers. It's a bit less unwieldy. It's a bit neater. It's not quite as crazy as factor trees. So I start with 676. It's even, so I know I can divide it by an even number. 2 goes into 6 3 times. 2 goes into 7 3 times with one remainder. 2 goes into 16 8 times. It's even again, so 2 can go into it again. 2 into 3 goes once with one remainder. 2 into 13 goes 6 times with one remainder. 2 into 18 goes 9 times. 169 is a bit of a tricky one. 2 won't go into it. You might know the little trick to see if something's divisible by 3. If I add together the digits, 1 plus 6 plus 9, that gives me 16. Because 16 cannot be divided by 3, that doesn't work. That means that 169 can't be divided by 3. So it's quite a handy trick. This only works for dividing by 3 or by 9. But hopefully some of you might recognise 169 is a perfect square, and 13 goes into 169 13 times. 13 goes into 13 once. So I can again find my prime decomposition from these numbers here is 2 squared times 13 squared. Now we can use these prime decompositions to solve some problems. So I want to find the highest common factor of these two numbers, and I want to show you how you can do this using the prime decomposition. So 676 we already saw could be written as 2 squared times 13 squared. Now 520, you might have a different number in your notes, but I have swapped it over, sorry. If we do the prime composition of 520, so again, primes that go into that, always easy to start with 2 for even numbers. 2 goes into 5 2 times, 1 remainder. 2 goes into 12 6 times, no remainder. 2 goes into 0, not at all. Still even, so we can divide by 2 again. 2 into 2 goes once, 2 into 6 goes 3 times, 2 into 0 goes 0 times. You could divide by 2 again because we've got the 0. I actually think in this case I'm going to notice 130 is the same as 13 times 10. So I'm going to divide by 13 because I think that's an easy thing to do at this step. 13 goes into 130 10 times. What else goes into 10? 2 goes in 5 times and 5 goes into 5 1 time. So my prime decomposition here is 2 cubed. I've got 3 2's, 1, 2, 3, times 5 times 13. Something to be aware of is that it doesn't matter which order you're choosing to divide. I chose to divide by 13 here. If I'd done 2 before, I still would have ended up with the same list of prime numbers. As long as you're always dividing by a prime, you will end up with the same answer. So what we then do is we put it together in a little Venn diagram. The factors of 676 and the factors of 520. So the factors in common, 2 squared, 2 cubed. So in common is a 2 squared. They both have a 2 times 2. 520 has an extra 2 factor, so that will go over there. 520 also has a 5, which 676 doesn't have. And they both have a 13, but 767 has an extra 13. When we do this, we get the highest common factor by multiplying what's in the intersection. So the highest common factor will be 2 squared times 13, which if the question asked us to, we could then work out in our calculator. We would leave it like this unless we're told otherwise. If we had to work it out, 2 times 13 is 26, 26 times 2 is 52, so that's our highest common factor. Now, this question doesn't ask it, but I might just show you while we were here, so we're aware. When we've got our two little parts like this, when we set up our factors, the part in the intersection here is how we get the highest common factor. And we can use this same diagram to get the lowest common multiple. We are looking at everything within the union of two sets, and that's how we get the lowest common multiple. So if I wanted the lowest common multiple of 676 and 520, I would multiply all of these numbers together. 13 times 2 squared times 13 times 2 times 5, which we could simplify as 2 cubed times 5 times 13 squared. I definitely can't work out that on my own without a calculator. If we wanted to see, we'd get 13 squared times 5 times 2 cubed. So we get the lowest common multiple is 6,760 in that case. let's do one last example, same idea. Use prime decomposition to get the lowest common multiple of 52 and 76. So we're doing the same process we just had before. 52, it's even, I'll divide it by 2. 2 goes into 5 2 times, 1 remainder. 2 goes into 12 6 times. Again, it's even, so I can divide by 2. 2 into 2 goes once, 2 into 6 goes 13. So, and 13 goes into 13 once. So 52 is equal to 2 squared times 13 squared. Same thing for 76 here. Even, I'll divide it by 2. 2 goes into 7 3 times, 1 remainder. 2 into 16 goes 8 times. Still even. 2 into 3 goes once, 1 remainder. 2 into 18 goes 9 times. This isn't a very exciting example by me, but this is what we've got. They're all prime numbers, we can't simplify more. If we put it into our little Venn diagram, 52 and 76, which factors are in common? Oh, sorry, there shouldn't have been. Just made a little mistake there. We didn't need that little 2. Okay. 2 squared is common to both. 52 also has a factor of 13. 76 also has a factor of 19. So therefore our lowest common multiple will be found by multiplying 13 by 2 squared by 19. And if we wanted to work that out as just a simple digit, by 2 squared is 4, by 19 we would get 988 is our lowest common multiple there. So that's how prime decomposition works. Now it's your turn to work on exercise 2E. As always, please take note of any questions and make sure you ask me about them when you see me next. Thank you very much for watching.